Hi, good morning, and welcome to the ZP Developer Zone. So we like to do this webinar, really answering technical questions. We sometimes do it twice a week these days because we do get a lot of technical questions. But that said, let me dive straight into it and just say today's the 28th of March. And as I say, it's really just answering technical questions that have come in during the week. The questions that we will answer today are about, on our website, we have what's called a copper deposition calculator, which calculates the kind of thickness of copper depending on the current that's passed. I mean, it's an approximation because there's all things like efficiencies of deposition, but you know, it at least gives people a rough sense of calculation. We're also going to talk about lactate monitoring. We did have an inquiry about lactate monitoring. We're super interested in lactate monitoring. In fact, I might even, I will mention this particular watch, which has been configured into a lactate sensor. It is using microneedles, so I will cover that today as well. And I will also cover very nice inquiry about aspartame and whether they can use a phenyl pyruvate oxidase enzyme. It's a really nice question, and the positive answer is yes, and I will discuss that as well. Plugging into a PalmSens potentiostat. Let's be clear, ZP is not doesn't distribute, doesn't manufacture PalmSens potentiostats, but we are happy enough to, this particular client does have, I think, I'm very biased. They have the world's best screen-printed electrodes. I know because they get them from us. The reason I say that they're the best is really the quality of repeatability. Both the raw signal, but the fact is our sensors are really repeatable. This is an example of one of our screen-printed electrodes here, so I'm happy to answer that, which actually then dovetails nicely into functionalization of screen-printed electrodes into an immunosensor, which is one of the last questions today that came through. So these are the 5 questions that I will be answering. I just want to say that there are 2 upcoming webinars that I think people should know about. We're doing one on commercialization of biosensors. So we do have a platform called SenseAll. To be frank, it's really good at translating research or get ideas into tangible electrochemical products. So we will be doing a webinar on that on the 23rd of April. We do one in the morning and one in the afternoon. If you're watching this webinar now, I'll put these links underneath the video on YouTube afterwards. Please sign up. Just know that we do this webinar every month. Don't worry about the January part there. I keep on updating the page to essentially reflect the new webinar. And we're also doing one specifically for academia as well, because I realized that, at ZP we do, the whole raison d'etre of ZP is really to translate electrochemical biosensing into commercial products, and we do it really for our clients. But I realized that kind of the starting stage for this is obviously academic research. We are doing a seminar specifically for academics. Again, that link is here. So if you're watching this, come to it, because we'll just go through stuff that's very specific to the academia part of the workflow. Just know that ZP also does, we do consulting, we do contract development, contract manufacturing. So if you're a commercial organization, you're interested in engaging with ZP, just know that we do have a commercial arm that specifically helps with companies. We do also do workshops on wearables, on IVDs. We do them every month, and we also do workshops on people's sites. Now let me jump into the question. So question number 1, copper deposition calculator. Okay, so this is something that we've probably had up since, well, I know it's pre-COVID, so it's probably about 2018. So they noticed that the electro calculator that we have, and they've got a link here, so you can find this electro copper plating calculator later on if you're so interested, that they say that I might have a mismatch between the centimeters and the micrometers by an order of magnitude, which I appreciate. See, this nice thing is that, when people kind of have given you feedback, it's useful because obviously feedback is actually part of quality control. So I did go to that calculator. I found it. I did sort of very sort of mechanically, not mechanically, but manually, I should say, look at it. So I looked at the thickness of deposition in centimeters, and I looked at the thickness of deposition in micrometers, and I literally counted the zeros. So 1, 2, 3, 4, 5. So I've got 5 zeros here. and there's 10 micrometers in 1 centimeter. So 10,000. So basically, I'm going to eliminate 4 of the zeros here, which will bring me to 1 0 here. So I just want to lay out why I think we are correct at ZP. Of course, I always take feedback. Hey, feedback is what makes us better in life, So just check me, and if I'm wrong, then fine, I'll take another look at that. But I think we've got it right. I might answer the question, why are we doing this? Why is ZP even interested in copper deposition? And it's actually because at ZP we are electrochemists, so we're very interested in electroplating. We're very interested in sensing and analytical technologies for electroplating. So we're very good at, for example, if somebody's trying to do a copper bath formulation, and they want to know that the copper bath formulation is good, or they want to know whether the additives that they are using are increasing or decreasing the rate of copper deposition, then ZP has a technology called SensiAll, which allows people to actually put samples of their electroplating formulation onto the sensor, and we can make an electrochemical measurement on that to kind of understand the quality of that plating bath, or understand whether inhibitors or accelerators in that copper plating bath are actually being useful, or what they're doing to the rate of copper deposition. So the reason we have that calculator up there is actually because of this SensiAll platform. If you're interested in SensiAll, just know that there is a webinar, and I just did talk about the webinar or something like slide 3 or 4 today. But just know that you can actually download the app for SensiAll on either the Google Play Store or the App Store. And we have different QR codes for different tests. Now that will be covered in this webinar on the 23rd of April. So please sign up for that webinar. And it doesn't matter if you miss it, because we do use the link, and every month we do a webinar at the end of the month anyway. So there will be ones in May, June, July, August, September, October, November, December, January, February, and then back around to March again. Question number 2 is about lactate sensing. Nice question. I like where the guy's coming from on this. We do wearable biosensors in many formats. This is a kind of just quick model of the skin. So the epidermis is actually just that top layer of the skin here, primarily dead cells. Underneath then you've got the kind of living tissue, which is your dermis. So if you scratch your skin and you kind of see the wet bits underneath it, then you're starting to get towards the dermis, and then you've got the subcutaneous tissue. Now, CGMs that are on the market today, I think, to be fair to Abbott, they've got something called the Abbott Freestyle Libre, probably 3 at this point. They've put a lot of money into marketing, so people are quite familiar with these kind of patches that that go on the skin. They put what they call, Abbott probably call it a filament, you can call it a wire, and it puts essentially an enzyme loaded wire into the body to measure glucose. There are companies working on microneedles. I said it earlier on, this is a microneedle technology. This one's had like 20 million spent on it, so this is not a low cost effort. ZP owns the tech here, and we have about 50 patents around microneedles. It's probably just worth saying on microneedles, our business model is to do contract development, contract manufacturing with other companies. So we are open to working with others on that. It's not our business model to go straight to the market. Something that I'm not covering here today, but if you maybe Google Zimmer and Peacock and sweat patch, you'll find this non-invasive form factor as well. And something that I will talk about today is implanted. You're not really going to do an implanted lactate sensor for human application. It's too invasive. You are going to do something kind of more minimally invasive, wearable type platform. That said, we do have this kind of tech. We're primarily using it in glucose and cortisol at the moment. But that tech is kind of fairly akin to what people are using as transdermal sensors for glucose. In fact, that tech has been actually implanted in these 2 fish. So these 2 fish are basically swimming around. There's no cables, etc. They're actually got these sensor packages embedded in them. But there we're just measuring the glucose. But glucose and lactate, technology-wise, they're fairly similar. There's a difference in the enzyme stabilities, but technology-wise, they're fairly similar. I don't want to extend it too far, but there's a question later on that somebody wants to measure another molecule using phenylpyruvate oxidase. And so some of what I'm saying now is also relevant to those people as well. So at ZP, we do have a lot of technologies around the measurement of lactate. And I've already shown you this particular watch. But this is something that has been formulated into a lactate sensor as well. But I think there's two sides to ZP. There's kind of what we can do with academia and there's what we can do with commercial organizations. But this kind of lactate watch technology is pretty cutting edge and super expensive to get into. We have done lactate monitoring in sweat. So that's why I'm sort of saying, oh, maybe you should Google Zimmer and Peacock and sweat lactate, because actually I haven't really covered it here. But we did actually get some really nice results, and I did line it up with some academic papers as well. I was really surprised by the correlation between what we did and what academia is doing as well. So we're either all wrong or we're all right. You know, it's sort of their data supports our data. And I do have a landing page here for some microneedle technologies from Zimmer Peacock. So hopefully that will be useful and interesting to you. Again, I'll put the links underneath the video as well. It was Aspartame. I was just trying to recall this earlier on. So this is a nice question. Question number 3 is, can they make a sort of a wearable or a biosensor technology for aspartame? This is aspartame. So I had a quick look at it, and they mentioned the enzyme phenylpyruvate oxidase, and I just looked at that molecule. I could see then the similarity between aspartame and phenylpyruvate oxidase. So I can see that those molecules would react with oxygen in the presence of the enzyme. I should put the enzyme on the arrow as well. What's really interesting is, I don't know if it's super interesting, but actually if you do in vitro work in a phosphate buffer, I can see this reaction running working because the phosphate is at least what for my reading is actually required. I know that there is phosphate in the body, but I'm not absolutely certain that there is phosphate, how much free phosphate there is circulating around the body. See, I know that phosphate is part of the sort of energy currency in the body, that you've got adenosine triphosphate, which, you know, is the storage of energy, and it becomes ADP, adenosine diphosphate. So I understand that phosphate is really important to the body, but I'm not sure how much, I don't want to say loose phosphate is around in the body or free phosphate is in the body. I'd love to hear any feedback if people know the answer to that. I just haven't looked into it yet. But what I'm saying is, if you do this enzymatic reaction in vitro as part of, let's say, a development program or something that's happening in university, you should get a signal because of the phosphate being in that buffer. But when you then translate it to the body, if you're trying to do wearables, that's one thing. If you're trying to do in vitro diagnostics on a platform like this, you could actually add the phosphate, so it wouldn't be so much of a problem. But if you were trying to do wearables like this, you'll have to find out how much free phosphate there actually is in the body. But that said, you can at least do a bench experiment, and I could see that, as you say, generating hydrogen peroxide. We do this kind of work all the time, where we take a electrode, we formulate an enzyme formulation. Oxidase is quite common, and we put what's called a barrier layer on it. I haven't linked to it, but we do have barrier layers on our website as well. And I can see that molecule reacting with the enzyme and actually generating hydrogen peroxide in the presence of oxygen. But I also have a suspicion you may need that phosphate anion as well, at least according to my reading. And you should actually be able to make a electrochemical biosensor out of that. So if somebody gave us that to do and said, oh, can you make a proof of principle for us on that? And then I'd be 100% sure that we could, from the reading that I've done. But the quick confirmation is, I think you can, at least in vitro on the bench in a phosphate buffer, probably achieve what you want to do. Question number 4 is very nice question. I've been supporting somebody on the integration between electrochemical sensors and lateral flow strips. I may have even put the wrong image up there, because actually I think they're actually using what we call our hypervalue carbon electrodes. But there'll be some links to our hypervalue carbon electrodes in a bit. They've got this Potentiostat, which is from PalmSens. Like I say, it's not something I super support these days, but you know, these are clients, so I'm happy to answer that question. What's happening is that they want to connect between our screen-printed electrode and their instrument. So they sent me some images, and I can see here, you know, I just wanted to kind of physically see what was going on here. So I can see their connectors here. These are called LEMO connectors. It's just a manufacturing brand, so I can see all that. And what I think is, I think these are, because I asked them whether they're using electrochemical impedance spectroscopy, EIS, and they've said yes, which tells me that I think PalmSens have two types of connectors, something they call the 4-pin and something they call the 5-pin. So when they have EIS capability, then I think they're then using a 5-pin connector. So obviously I'm not the manufacturer or distributor of this product, so this is just kind of my observations or my looking at their product. But we have made cables from in the past. The thing about making cables that go on other people's equipment is that if they update, then you don't always know about it. They've also sent me some pictures of their connectors. This is the PalmSens connector. Now, I will show you that the PalmSens connector, for some reason, doesn't make good connection with ZP screen-printed electrodes. So you do have to use a ZP connector. I'll show you some data on that in a minute. Because theoretically, I would... this connector, there's some pins in here. We've got 1, 2, and 3 here. Those pins line up with ZP screen-printed electrodes, but for some reason they don't press hard enough. They don't give us a good enough electrical connection. So those pins theoretically will line up. I'll show you the problem that we have. It doesn't mean you shouldn't try, but I'll just show you the problems that we had and maybe discuss it. Next to it is another type of connector. It's from Micrux. That's got 4 pins in it. I can't make any comment on that. I'm not really familiar with this connector at all, but I just want to observe that I have seen what you've sent me and I have recognized it. The PalmSens theoretically should work, but we tried it in the past and we were expecting like these beautiful results with a particular client, but actually what they were getting was this, which was it was due to a poor connector. So they were using this. So it ended up meaning that we actually ended up making a connector for them. And that was the birth of the connector that we actually sent to you guys. So this was the birth of that connector. But I understand that that connector covers too much of the screen-printed electrode for you. You want to have the connection a bit lower down on that device. So I understand that. So this connector does work really well with our screen-printed electrodes. I'll put a link to it, but that's 7mm. Is because the width of our screen-printed electrodes is 7mm, and Potentiostats like PalmSens often use 2mm banana plugs. So that's why the 7mm and 2mm are in that name. So it will work with those 2mm banana plugs that are on PalmSens. So we do have a cable, and it's called the LEMO 5 and SPE7. So that tells me that that connector is ready for our SP screen-printed electrodes, 7mm wide screen-printed electrodes, and that's the LEMO 5-pin connector there. So I think that cable will work for you. So that will go into the machine, and that obviously will go into the screen-printed electrode. Question number 5, immunosensors on a screen-printed electrode. So this is a nice one. This is coming from France. Beaucoup de gens en Zimmer Peacock parlent un petit peu en français, mais je parle seulement en anglais maintenant. So it's nice that you found the screen-printed electrodes interesting. You were thinking about making your own screen-printed electrodes. We did this the other day. This is a shot of a ZP screen-printed electrode. This is our 501 carbon electrode. I really, zoomed in on it because I really like the quality, the crispness of our print. And this is no criticism of this, but this is something that somebody, I think, has made in-house. And it's the biggest problem with in-house production of screen-printed electrodes. This one actually had a bit of a problem that's actually shorted here. But that's probably easily avoidable. I mean, what's happening is the ink is spreading too much, but there's no crispness on it. The problem with that is it's not going to have good reproducibility. If you don't have good reproducibility on screen-printed electrodes, you're going to have you're stuck. You cannot it's hard to do any kind of good quality science unless the underlying screen-printed electrodes or materials are reproducible. So it's nice that you were thinking about using our electrodes. You do ask a question, can you use an oscilloscope? I've had this before with people where they try to use instruments that are really designed for the electronics world to drive electrochemical sensors. So an oscilloscope really is, you know, for kind of characterizing for characterizing electronic components or electronic systems. So electrochemical, you know, I understand there's an electro in there, but I really think that you spend more time trying to make the instrument work than actually moving the science forward. So my strong advice to you is don't try and use an oscilloscope. You're just going to spend more time trying to get the whole thing to work rather than actually moving any sort of science forward. There's a simple paper here actually. So I'm going to answer your question about how do you functionalize. So I've got a link here. The link will take you to a particular paper. I am an author on it. I like this paper because it's quite simple to do. Now you can use our 501 carbon electrode actually to do this, but I'll have a link to that in a minute. But we just use something called pyrene NHS. It sticks to the carbon quite well. That allows you then to stick the covalently bond the antibody, if that's what you're going to use, and then you can use chitosan to block, and then you can wash the whole thing down. If you read the paper, you'll find out that we follow the process using a technique called cyclophotometry. That's why that oscilloscope, see, it doesn't have the kind of techniques, or it doesn't easily have the kind of techniques that you would otherwise need to do this kind of work. So I can't really recommend that you try to do this with an oscilloscope. I love electronic instruments, so it's not like from a position of not liking them. It's just, it's not the right tool for this kind of work. That said, you can make the assay itself work then by differential pulse voltammetry. I understand that the three techniques that work quite well with immunosensors are differential pulse voltammetry, square wave voltammetry, and electrochemical impedance spectroscopy, EIS. So I can understand why that oscilloscope is in your mind, but you really need a potentiostat probably with impedance spectroscopy capability. When I'm doing this kind of work, or when we're doing this kind of work, we like to use a reporting molecule. I think we're using something like ferricyanide in the paper, and as we add in the antigen, then the signal changes accordingly, and we actually got quite a nice signal in that particular piece of work. Rather than jumping into an unknown antigen antibody format, I'd actually just repeat the paper in your first instance. By repeating a paper, it kind of baselines you, make sure that, you know, everything is working okay. Then you can start creating novelty on top of that. I put a link here, in fact, but the reason I'm glad that you're thinking about using ZP electrodes is they are by far, I absolutely know this, that, you know, we make the world's best screen-printed electrodes, at least in terms of repeatability, because you will not get a bad screen-printed electrode from ZP, and the reason being is that ZP uses our screen-printed electrodes all the time in all of our products. We're using it all the time, so we kind of, you know, we're a line of defense between you and bad materials, because actually we're the first ones to use them. And then we do have what's called an OQC, an outgoing quality control, where actually we do a lot of electrochemical testing of screen-printed electrodes to make sure that they're actually good. The kit you'll need is that paper. So there's a link, I'll put a link to the paper. You'll probably need the 501, you'll need a connector, you'll need a cable, and you might need a potentiostat, but I'll put those links here as well. You're probably, I mean, if you're in France, there's plenty of potentiostats at universities, but that's the key word. Don't use that oscilloscope. I really think you're going to spend more time trying to figure out that oscilloscope. It's not designed for this kind of work. You know, they're good instruments, but they're really for electronic characterization, not for electrochemical experimentation. So question number one is about copper deposition. I think I've checked that calculation. I have manually counted the zeros. I'm pretty sure I got it right. Lactate monitoring. Hopefully some of those pages and links will be useful to you. Aspartame. If you do this in the lab using a phosphate buffer, it should work fine. Plugging into the PalmSens, there's a LEMO 5-pin cable for a 7mm SPE. Hopefully that's the right one for you. Functionalizing a screen-printed electrode. There's an easy paper to follow. Hopefully you can follow that. So if you've got any questions on ZP, don't hesitate to reach out to us. As you can see, we do try to answer every question in a fair amount of detail, and we record it so you can rewind it, and I'll put the links underneath the video as well. Okay, thanks very much.